The concat function in SQL is used to combine, or concatenate, two or more strings or values into a single string. It takes multiple inputs, such as column values, literal text, or expressions, and joins them together seamlessly, producing a unified output. This function is particularly useful for creating readable and meaningful outputs by combining data from different columns or adding custom text. Concat, string 1, string 2, up to string n. String 1, string 2, up to string n are the inputs to be combined. These can be column names, like name, city. Literal strings, text as, lives in, between quotes. Other expressions that evaluate to strings. The function returns a single string that is the result of concatenating all inputs in the order provided. Consider the following SQL query. Select concat, name, lives in, city, as info from names. This query takes the name column from the names table. Appends the literal string lives in, note the spaces for proper formatting. Appends the city column from the names table. Combines these into a single string for each row in the names table. The result is a new column in the output, named info, due to the as info clause, with values like Alice lives in New York. The as keyword renames the output column for clarity. In this example, as info names the concatenated result info. Without it, the column name would default to concat, or a system-generated name in some databases, which is less descriptive and could confuse users interpreting the output. The string lives in is a literal text value enclosed in single quotes. The spaces at the beginning and end are intentional. The leading space ensures proper separation between the name, Alice, and the text, lives in. The trailing space ensures separation between, lives in, and the city, New York. For example, without these spaces, the output would look cramped, Alice lives as one word, and Inu as one word. Null values. In many SQL databases, if any input to concat is null, the entire result is null. Other databases may treat null as an empty string in concat, so the behavior may vary. Best practices. Always include appropriate spaces in literal strings to ensure readable output. Use coalesce or similar functions to manage null values gracefully. Use as to give meaningful names to concatenated columns. Be aware of differences in concat behavior, like null handling, across SQL databases. By mastering the concat function, you can create more informative and user-friendly outputs in your SQL queries, making your data easier to understand and present. Select concat, names.name, quote space, is, space quote, ages.age, quote space, years old, and lives in, space quote, names.city, as details. From names. Inner join ages on names.id equals ages.id. The query uses the concat function to combine multiple strings and column values into a single, readable output string. It joins data from two tables, names and ages, to create a descriptive sentence about each person, including their name, age, and city of residence. It creates a single string for each row, forming a sentence like, Alice is 25 years old and lives in New York. Names the output column details using the as keyword for clarity. The concat function in this query combines the following components. Names.name, the name column from the names table, like Alice. Is, a literal string with a leading space, to separate the name, and a trailing space, to separate from the age. Ages.age, the age column from the ages table, like 25. Age is assumed to be a numeric type, which SQL automatically converts to a string for concatenation. Years old and lives in, a literal string with a leading space, to separate from the age, and a trailing space, to separate from the city. This provides context and ensures readability. Names.city, the city column from the names table, like New York. The as details clause renames the output column to details, making it descriptive and user-friendly. Without this, the column might be named concat or a database-specific default, which is less intuitive. The concat function is particularly useful for creating dynamic, human-readable outputs directly within SQL queries. This explanation examines the select statements, highlighting the importance of spacing, number handling, and the power of concat. As you can see in the first statement, there are spaces around lives in. If these spaces were missing, so if you would type lives in with the quotes around it but without the leading and trailing spaces, you would get two words. Carol lives is the first word, no spaces in it, then we get the space we put between lives and in, then we get our second word, in Chicago, as one word. So keep the spaces in mind when you are using concat to add text or numbers. Good that I mentioned numbers. With concat, numbers are also considered to be text. So, if you want to change lives into lives 5 years in, you have to enclose that entire line in quotes, including the numbers and spaces. Concat is a powerful tool for dynamically generating emails directly within SQL. Instead of importing data into, for instance, PHP just to build and send an email, why not let the database handle it? Many relational databases support email functionality either natively or through extensions. Even better, you can automate the entire process with triggers. For example, when an important event happens, such as a large transaction, a failed payment, or a new customer sign up, a trigger can generate and send an email immediately. Since you would have to configure email settings in PHP anyway, why not keep everything inside the database? Transforming text with upper and lower. The upper and lower functions transform text by converting it to uppercase or lowercase, respectively. These functions are useful for standardizing data, improving readability, or preparing text for display. Select upper, name, as uppercase _ name, lower, city, as lowercase _ city from names limit to. What the query does. Upper, name, converts all characters in the name column to uppercase, Alice becomes Alice in all uppercase letters. Lower, city, converts all characters in the city column to lowercase, New York becomes New York in all lowercase letters. As uppercase _ name / as lowercase _ city, renames the output columns for clarity. Limit to, restricts the output to 2 rows for brevity, ideal for demonstration. You can also change parts of words, or even single letters, to uppercase or lowercase. But, in order to do that, we need to go back to concat again. In Postgres, another way to combine strings is the double pipe, the concatenation operator. It works similarly to concat, but with one key difference: the double pipe does not ignore null values. If any part of the concatenation contains null, the result will be null. Note, concat treats null as an empty string. The writing can be different between relational databases, and the behavior can also be different. So, always check the documentation for your RDBMS, as syntax and behavior differ. Trial and error is a practical way to learn these nuances. Again, this is why I strongly recommend experimenting with different database management systems. While the double pipe is the concatenation operator in Postgres, it may not work the same way, or at all, in other databases. The best part is that you can test these differences at home. Many database systems are free to download and use. Take notes of the variations you encounter. You do not need to memorize them all, but having a reference on your laptop can save you time when working with different databases in the future. Back to concat. Select hello double pipe, quote space quote, double pipe world. There is a space between the two quotes in the middle. The output is, hello world, the two words separated by a space. Select hello double pipe null double pipe world. The output is null. Transforming specific letters in Postgres. Postgres, as do most database systems, provides powerful functions like left, substring, upper, and lower. Combined with the double pipe operator, you can transform specific parts of a string, such as changing only certain letters to uppercase or lowercase. Change only the third letter of the word database to uppercase. Select left, database, 2, double pipe, upper, substring, database from 3 for 1, double pipe, substring, database from 4, as result. Result is, database, with a capital T. I explain this on the next slide. Capitalize the first letter, lowercase the rest. Select upper, left, name, 1, double pipe, lower, substring, name from 2, as formatted _name from names, limit 2. What happens here is that we extract the name from the names table. We take the most left position, left name, 1, that means only the first character from the left. Upper changes the character to uppercase. Next, we extract all the other characters from position 2, subtracting name from 2, till the end. Lower changes the characters lowercase. As a final step, we concatenate them back to the name. So, the result is, formatted _name, Alice, Bob with a capital first letter. Best practices. Use clear aliases, use as for meaningful column names. Include spacing, when concatenating, ensure proper spacing in literals, not needed in our examples. Test transformations, verify output for edge cases, like short strings and null values. Cross-database note, left, substring, upper, and lower are standard, but the double pipe is Postgres specific. Other database may use concat or the plus sign. Back to our statement to capitalize the third letter with Postgres. You can see the query in the previous slide. Select left, database, 2, upper, substring, database from 3 for 1, substring, database from 4, as result. We have the word database. And let us see what happens with it. We start with left, database, 2, this extracts the first two characters from the word database, that is, DA. Next we have upper, substring, database from 3 for 1, this extracts the third character, T, and converts it to uppercase, a big T. Then we have substring, database from 4, this extracts everything from the fourth character onward, that will be, a base. Finally, the database concatenates them together to database. All lowercase letters but a capital T. And again, this is for Postgres. Select substring, hello world, from 1 for 5, this is Postgres specific, the query returns hello. Most other databases use. Select substring, hello world, 1, 5, this query also returns hello, but for instance in MySQL. In this slide you see the input and output from our previous select statements. Select upper, name, as uppercase _name, lower, city, as lowercase _city, from names, limit 2. This returns the first two rows. Uppercase _name, Alice, Bob, lowercase _city, New York, Los Angeles. As you can see, Alice and Bob are in uppercase, while New York and Los Angeles are in lowercase. Select upper, left, database, 1, substring, database from 2, as result. The result is database. Here we take the first letter on the left and change it to uppercase, the rest remains lowercase. The result is the word database, but with a capital D on the first left position. Select left, database, 2, upper, substring, database from 3 for 1, substring, database from 4, as result. Result. Database. We have seen this one in the previous slide, the third letter has changed to uppercase T. Select upper, left, name, 1, lower, substring, name from 2, as formatted _name from names limit 2. formatted _name, Alice, Bob. And this one we have seen too, both names start with a capital letter, the other letters are in lowercase. Please remember, this notation is specific for Postgres, it will most likely not work in other databases. Let us take a last look at left, right, and substring. Left, string, length, returns the first length characters from the start of the string. Select left, database, 4, this returns the first 4 characters from the left, data. Right, string, length, returns the last length characters from the string. Select right, database, 4, this will return base, the 4 characters on the right. Substring, string, start, length, extracts a portion of the string, starting at a specific position. Select substring, database, 3, 4, returns to B. As we know by now, this is not the same for all databases. For Postgres, you would use select substring, database from 3 for 4, to return to B. In this case it works too with 3, 4, but I strongly recommend you to stick to the Postgres way of writing. So once more, if you receive error messages or you get unexpected results, check the documentation of your specific database system. Completing joins, the cross join. The cross join is a type of join that combines every row from one table with every row from another table, creating a Cartesian product. It is rarely used but useful for specific scenarios. How it works. It pairs each row from the first table with every row from the second table. The total number of rows is the number of rows in the first table multiplied by the number of rows in the second table. Unlike other joins, inner, left, cross join does not require a matching condition. Use cases. Testing combinations, generate all possible pairings. Data generation, create sample data for demonstrations. This join is often avoided due to the large result sets. The output size can grow rapidly, as 100 rows times 100 rows equals 10,000 rows. Use limit or filters to manage large results, as cross-join can be resource-intensive. Cross-join in action. The cross-join combines every row from 2 tables, creating a Cartesian product. Let us see it in action with a simple example and understand its impact. Select names.name, ages.age. From names. Cross-join ages. The result is Alice 25. Bob 25. Carol 25. Alice 30. Bob 30. Carol 30. Alice 40. Bob 40. Carol 40. What is happening? Cartesian product, each row in names, 3 rows, pairs with every row in ages, 3 rows, producing 3 times 3 equals 9 rows. This is from when my names table only had 3 records. No on condition, the cross join does not require a matching condition, unlike inner or left join. Best practices. Limit results, use limit or filters to manage large data sets. Document usage, comment cross-join queries, as they are uncommon and may confuse others. Verify across databases, cross-join is standard, but always check syntax for your RDBMS. Understanding query optimizers in Postgres and MySQL. In this guide, we dive into the query optimizers of Postgres and MySQL, building on our earlier introduction. A query optimizer is a core component of a database management system that determines the most efficient way to execute a SQL query. It evaluates multiple execution plans, considering factors like table size, indexes, statistics, and system resources, and selects the plan with the lowest estimated cost. While both Postgres and MySQL have robust optimizers, their approaches differ in complexity and capabilities. Let us explore how they work, how to interact with them, and why regular practice is key to mastering their output. Postgres Query Optimizer. The Postgres optimizer is renowned for its sophistication and ability to handle complex queries, such as those with multiple joins, subqueries, or window functions. It uses a cost-based optimization approach, relying on detailed statistics about table sizes, column distributions, and index usage. These statistics are collected via the analyze command, which enables accurate cost estimates for operations like scans, joins, and sorts. To inspect the optimizer's chosen plan, Postgres provides explain and explain analyze, which reveal estimated costs, actual execution times, and index usage. MySQL Query Optimizer. This optimizer is designed for simplicity and speed, especially for read-heavy workloads. It also uses a cost-based optimizer, but it is generally less sophisticated. The statistics are updated via analyze table, however, they are less granular, which can lead to less accurate cost estimates for complex queries. It struggles with complex queries involving multiple joins or subqueries. It may take longer to plan queries with many tables or fail to find the optimal plan. MySQL provides explain and explain analyze, but the output is less detailed. MySQL Query Optimizer. The MySQL optimizer prioritizes simplicity and speed, making it well suited for read-heavy workloads, such as web applications. It also uses cost-based optimization, but its approach is less sophisticated, especially for complex queries involving multiple joins or subqueries. Statistics are updated with the analyze table command, but they are less granular, which can lead to less accurate cost estimates. Explain and explain analyze provide insights into the query plan, though the output is less detailed. MySQL may struggle to find optimal plans for queries with many tables and is less aggressive in reordering operations compared to Postgres. Both optimizers may rewrite queries to improve efficiency, but the Postgres optimizer is more likely to reorder joins or apply advanced optimizations. To effectively use query optimizers, you should regularly run explain or explain analyze on your queries to understand their execution plans. Optimizer output can seem cryptic at first, but regular use builds familiarity with terms like sec-scan, cost, or rows. By comparing estimated and actual metrics, you can identify when statistics are outdated or indexes are needed. Optimizer behavior evolves with database updates, so always check the official documentation if the output looks unfamiliar or changes after an upgrade. Using the optimizer, an example. Let us see how the optimizer works with a simple query in Postgres. Select asterisk from names. Inspect the query plan. Use explain to see the optimizer's plan without running the query. Explain select asterisk from names. Output. Sequential scan on names, cost equals 0, 13, rows equals 300, width equals 240. Sequential scan, the optimizer chose a sequential scan, reading all rows in the names table. Cost equals 0, 13, the estimated startup cost, 0, and total cost, 13. Rows equals 300, the optimizer estimates 300 rows will be returned. Width equals 240, the average row size in bytes. This output shows the optimizer's initial guess, which may be inaccurate if table statistics are outdated. To see more details, including actual execution times, use explain analyze to execute the query and see actual performance. Explain analyze select asterisk from names. Output. Sequential scan on names, cost equals 0, 13, rows equals 300, width equals 240, actual time equals 0.065, 0.068 rows equals 8 loops equals 1. Planning time, 0.231 milliseconds. Execution time, 0.134 milliseconds. Actual time equals 0.065, 0.068, the query took 0.065 milliseconds to start returning rows and 0.068 milliseconds to complete. Rows equals 8, only 8 rows were actually returned, compared to the estimated 300. This suggests outdated statistics. Loops equals 1, the operation ran once. Planning time, time to generate the plan, 0.231 milliseconds. Execution time, time to execute the query, 0.134 milliseconds. The mismatch between estimated, 300, and actual, 8, rows indicates the optimizer needs better statistics. Update statistics. Analyze names, generates no output. This updates statistics about the names table, such as row counts and value distributions. After updating statistics, check the plan again. Second run. Explain select asterisk from names. Output. Sequential scan on names, cost equals 0, 1.08, rows equals 8, width equals 18. The estimated rows, 8, now match the actual table size, and the cost, 1.08, is lower, reflecting a more accurate plan. The width, 18, is also corrected, indicating a more precise estimate of row size. Run with explain analyze to confirm. Explain analyze select asterisk from names. Output. Sequential scan on names, cost equals 0, 1.08, rows equals 8, width equals 18, actual time equals 0.039, 0.042, rows equals 8, loops equals 1. Planning time, 0.189 milliseconds. Execution time, 0.065 milliseconds. The estimated and actual rows, 8, now align, and the costs and times are consistent. The lower planning and execution times reflect the optimizer's improved accuracy after updating statistics. This example shows how the optimizer's decisions depend on statistics. Without running analyze, the initial plan overestimated the row count, which could lead to suboptimal plans for more complex queries. Regularly using explain and analyze helps you verify the optimizer's assumptions and ensure efficient query execution. Tips. Practice regularly, run explain on your queries weekly to build intuition for reading plans. Start with simple queries like select asterisk from names and progress to queries with where, join, or group by. Check documentation. If the output includes unfamiliar terms, as index scan, hash join, consult the documentation to understand new behaviors, especially after database upgrades. Update statistics, run analyze after significant data changes to keep optimizer estimates accurate. Compare plans, use explain analyze to compare estimated versus actual metrics and identify when indexes or query rewrites are needed. In general, databases automatically update their statistics, so you typically do not need to run analyze manually. That's a wrap for this lesson. You have mastered the cross-join, concat, and transforming text. Great work. In our next video, we will dive into constraints. Keep practicing to solidify your skills, and I see you in the next lesson.